The video you are watching now is no longer part of the present, it belongs to the past. And even if you are watching me live, the light emitted by your screen does not immediately reach your eyes. The light from this video had to travel and cross space, but it did so at a certain speed, and the consequence of this is that you, in a way, are stuck in the past. You will never be able to see things as they happen. It's as if the entire universe and what happened in it were just a movie for you. And this fact, that light takes time to travel through the universe, is a crucial factor for astronomy, so much so that we created a special unit for it, the light year. But the light year is not a measure of time. It actually measures the distance that light travels in 1 year, and this number is gigantic. The speed of light is 299,792,458 meters per second, and that is very fast when we compare it to the speed scales we are used to, because in just 1 second, a beam of light could circle the Earth almost 8 times, but at the same time that light seems fast, it is extremely slow when we think about cosmic distances. Recently, I took this photo of the Trifid Nebula using my telescope. What we are seeing is, in fact, the Trifid Nebula, but 5,200 years in the past, which is the time it took for the light emitted by it to travel all this way until it ended up on my camera's sensor. What a horrible journey. And when I saw the result of the photo, I couldn't help but wonder how this nebula is now, in the present, at this exact moment. But this is a question we will never be able to answer, because we are hostages to the speed of light, which is extremely slow on universal scale. And to make matters worse, nothing can move faster than light. But why? Why does the universe have a maximum speed in the first place? And Galileo was one of the first people to try to measure the speed of light. Fast, but not infinite. Suggested there say, directory hemwine, where also a dining health came for mothers. And for that, 2 volunteers held lanterns, both on top of hills that were a certain distance away. With the lanterns covered, each would reveal their lantern, while the other would try to time how long it took for the light to reach them. And since no delay was recorded, Galileo's conclusion was that the speed of light was infinite, at least in practice, because he suspected that it would actually be so fast that no human experiment would be able to measure it. But in this, Galileo was wrong, and the one who showed us this was the astronomer Romer. He discovered that not only did light have a speed, but it was also extremely relevant, at least for observations of Jupiter's moons. Romer noticed that the time Io spent behind the planet Jupiter depended on how Earth was moving in relation to the planet. He noted that when Earth was moving away from Jupiter, Io seemed to stay behind the planet for 22 minutes longer than when Earth was moving towards it. This led him to the conclusion that the best way to explain this difference was the fact that light did have a speed and that it took some time for Io's light to reach Earth after emerging from behind Jupiter. And he even managed to understand that when Earth was moving away from Jupiter, light needed to travel 22 minutes longer to reach us. This made him the first person to almost succeed in measuring the speed of light. His calculations resulted in around 210,000 kilometers per second, which is almost 60% of the correct value. And almost 100 years later, the English astronomer James Bradley achieved a slightly more precise value for the speed of light, very close to the current one in fact, and he estimated that light moves at 300,000 kilometers per second, which is basically correct. Have you ever noticed how just one opportunity can completely change the course of your career? But to get there, it's not enough to just have skill and knowledge. It's necessary to understand what the market really looks for. And that's why Allura launched the Tech Hitchhiker's Guide 2025, your passport to the best tech jobs in Brazil and abroad. There are more than 20 free materials gathered in one place: resume templates, interview strategy, salary guide, and the coolest part, a masterclass to help you build an international career. All of this was done in partnership with recruiters and mentors from Allura's Talent Lab. So don't miss this chance. Download the guide from the link in the description or in the pinned comment and start planning your next step in the tech world now. Romer and Bradley were responsible for the first modern steps to understand the speed of light, Maxwell and light, and centuries of experiments with optics revealed more and more details of its behavior. But despite this brilliant effort, the true nature of light remained a mystery. So much so that at the beginning of the 19th century, the most popular theory was the theory of the luminous ether. This was the idea that the universe was filled with some kind of super light matter called ether, and it is vibrations in this ether that we perceive as light. That is, in the same way that when we throw a stone into a lake, we see ripples in that lake, producing light means making the luminous ether ripple. But even with several theories being proposed all the time, no experiment could understand exactly what light was. And as a kind of historical plot twist, The true nature of light was found not with an experiment, but at the tip of the pen of the physicist James Clerk Maxwell. Today we call the results obtained by him the 4 Maxwell's equations. But the most curious thing about this story is that a 5th equation can be obtained by combining all of Maxwell's equations. And this 5th equation predicts the existence of a wave formed by electric and magnetic fields. And this wave travels at a speed determined by the fundamental constants of electromagnetism. And I will call this speed c. And it is a constant. Do you see where I'm going with this already? The constant c is determined by 2 other important values for electromagnetism. The electric permittivity of free space, which determines the intensity of electric fields in a vacuum, and the magnetic permeability of free space, which is kind of the same thing, but for magnetic fields. And if I were in the 19th century, like Maxwell, I would say ether instead of vacuum. And as I will explain later, perhaps the idea of ether was not so wrong after all. The important thing is that Maxwell discovered an electromagnetic wave with a speed c based on the laws of electromagnetism. And this speed c is exactly the speed of light. That is, by studying electric and magnetic fields, Maxwell inadvertently discovered the nature of light, which is a specific combination of electromagnetic fields. And with that, now we are close to answering some of the main questions of this video. The first of them is, why does light have this speed that we call c? The answer is because this is the predicted speed for electromagnetic waves, as determined by the permittivity and permeability of vacuum, okay? But why do they have the values they have? That's an excellent question, and I'll answer that shortly. But for now, what we still need to answer is, why is the universe's speed limit the speed of light? Albert Einstein and light. To understand the answer, first we need to understand 2 aspects of Albert Einstein's theory of general relativity. The first part is the second postulate of relativity, which states that the speed of light in a vacuum is always the same for all observers, regardless of the movement of the light source or who is observing it. We know today that this idea is true, but it is still absurd. Let's imagine that you are stopped in a car and throw a small ball forward at 20 kilometers per hour. What is the speed of the ball for someone standing on the sidewalk? 20 kilometers per hour. Now, let's imagine that you throw the same ball at the same speed, but while driving in a car at 100 kilometers per hour. Now, what is the speed of the ball for someone standing on the sidewalk? 120? Higher. 120? Correct. 120 kilometers per hour. Good to know I work with the right people. 120 kilometers per hour, which is the sum of the car's speed and the ball's speed. But what the second postulate of relativity says is that if this ball were in fact the light from a flashlight, in both scenarios, the light would have the same speed, which would be the speed of light in a vacuum. And this is very strange because it means that everything you understand by speed kind of doesn't apply to the speed of light. The speed of light in a vacuum is absolute. And for this to always be true, almost all the laws of physics discovered since Newton need to be altered. And a consequence of these new laws of physics is that accelerating an object to the speed of light costs infinite energy. And since there is no infinite energy, no object can move at the speed of light. So why is the universe's maximum speed the speed of light? Because the speed of light needs to be constant and absolute. And for that to be true, it must be impossible to move faster than light. And if you follow this channel, you've probably heard this explanation before. But what I bet you've never heard is the next part. What I just said is somewhat imprecise. The statement that nothing can move faster than light are in fact 2 facts mixed into one. And the 2 facts are, first, the universe has a maximum speed, which is the speed we call c. Second, light moves at the universe's maximum speed. What this means is that the real question I want to answer is not why the speed of light is the universe's maximum speed, but rather, where does this speed c come from? Because if I've done a good job so far in this video, you've understood that this speed is not the speed of light. It is light that has this speed that we call c. I really hope that was clear. The constant c precedes the idea of light, and a clue to its origin is in another famous contribution by Einstein, E = mc squared. This equation represents one of the deepest facts of relativity. Matter and energy are the same thing, but in different forms. Putting it another way, it is possible to transform energy into matter and matter into energy, and this conversion has an exchange rate. What this famous equation tells us is how much 1 unit of energy is worth in terms of matter. And the answer is that 1 unit of energy is equivalent to the constant c squared in matter. Energy equals matter times c squared. The curious thing here is that E = mc squared is an equation that uses the speed of light, but has nothing to do with speed or light. And this shows that the constant c is something that is more fundamental than the speed of light. So, when we ask ourselves why light has the speed it has, we should should actually ask ourselves, what is the true origin of the constant c? The 100% honest answer is that we are still not sure. 1542c. Physics, like all science, is not ready in the sense of being finalized. We have excellent theories that make precise predictions about the behavior of nature, but these theories depend on constants that have values that, most of the time, we don't know how to explain properly. And two of these constants are precisely those I just mentioned: the permittivity and permeability of vacuum, which are the electromagnetic constants that precisely determine the value of c. So, is it possible to explain the value of these two constants and discover the origin of the universe's maximum speed? Some people are trying. One of the most interesting recent results comes from an article published in 2013, a year before the 7-to-1. In this article, the group of researchers tried to calculate the correct values of the permittivity and permeability of vacuum based on quantum field theory. In practice, what this means is that they tried to explain the origin of the speed of light based on more fundamental ideas, and in the process, they tried to unify the speed of light with other aspects of nature, such as quantum physics. And it is this process of unifying seemingly separate ideas that has been responsible for all the great revolutions in physics. So the research project is promising, and if you want to understand what the article proposes, what exists is the vacuum, and on average, the vacuum is perfectly empty. Nothing is happening. But remember, this is on average, and the average doesn't always happen. Even in the absence of matter as we know it, our universe is filled with what are called quantum fields, and you can think of these quantum fields as a lake. For the most part, the lake is perfectly calm and smooth, without ripples. This would be a quantum field without energy. Now, if a stone falls into the lake, waves will form. Similarly, if something shakes a quantum field, we see particles. The particles are perturbations in the fields. And now that we understand this, we just need one more detail. Just as a lake always has small ripples, which are usually not visible until we get very close, the vacuum is also not perfectly still. There are always small ripples in the quantum fields. And to simplify the calculations, physicists interpret these small ripples in the fields as ephemeral particles, which are pairs of particles that arise in the vacuum and then annihilate each other. On average, nothing is still happening, but at every small instant there are at least some particles appearing and disappearing, like the small ripples of a lake. And now try to imagine a beam of light crossing this vacuum, with ephemeral particles appearing and disappearing. And the main detail here is that we will not attribute any speed to this beam of light. You can say that it moves at any speed, including much faster than speed c. We can even assume that the beam of light with infinite speed will bump into the ephemeral particles of the vacuum, and these bumps will delay the beam of light. And by doing the math, it is possible to calculate that the speed of light in a vacuum is exactly the constant c. Oh, the universe and its mysteries. That is, the result of the article is to connect the speed of light and the electromagnetic constants with the properties of the quantum vacuum, which is incredible. A similar logic was used to deduce the electromagnetic properties of vacuum, both permittivity and permeability. Okay, so does that answer what the true origin of the constant c is? Not completely. The article only explains one aspect of this fundamental constant, which is its connection to the speed of light. But why, for example, does it appear in the equation E equals mc squared? We don't know, and that's good. A good physical theory will never just give answers, but rather find new questions to be explored. So, why does light have speeds? Probably because it bumps into particles appearing in the vacuum all the time. And why can nothing move faster than this speed? Because as far as we know, Einstein's relativity is true, and the theory predicts this. And where does this mysterious constant come from? How do the vacuum fluctuations of space connect with the constant c? Nobody knows yet, but I hope that with this video, we are all one step closer to the answer. To truly grasp the magnitude of this mystery, we must delve deeper into the fabric of reality itself. The concept of the quantum vacuum is not merely an abstract mathematical tool, it is the very foundation upon which our universe is built. When we speak of ephemeral particles, we are talking about virtual particles that borrow energy from the vacuum for a fleeting moment before returning it. This continuous boiling sea of quantum fluctuations means that empty space is never truly empty. It is a dynamic, energetic arena where the laws of physics are constantly being tested and enforced. The interaction between a photon, the fundamental particle of light, and this quantum sea is what ultimately dictates the speed limit of the cosmos. Every time a photon travels through space, it is essentially navigating an incredibly dense obstacle course of virtual particles. These interactions, though infinitesimally brief, collectively act as a drag on the photon, ensuring it can never exceed the speed c. This elegant mechanism not only explains the constancy of the speed of light, but also beautifully ties together the macroscopic world of relativity with the microscopic realm of quantum mechanics. Furthermore, the implications of this speed limit extend far beyond mere travel times. The speed of light is intimately connected to the concept of causality, the principle that cause must precede effect. If information or matter could travel faster than light, it would be possible to construct scenarios where an effect occurs before its cause, leading to logical paradoxes that would unravel the very fabric of reality. Imagine receiving a reply to a message before you even sent it. Such paradoxes are prevented by the absolute nature of the speed c. It acts as a cosmic referee, ensuring that the sequence of events remains consistent for all observers, regardless of their relative motion. This is why the speed of light is not just a number, it is a fundamental structural pillar of the universe. It defines the boundaries of what is possible and what is not, shaping the evolution of galaxies, the life cycles of stars, and the very existence of life itself. As we continue to probe the depths of the universe, our understanding of these fundamental constants will undoubtedly evolve. New theories, such as string theory or loop quantum gravity, attempt to provide a more comprehensive framework that could finally explain the origin of the constant c and its relationship with the other forces of nature. These theories suggest that at the smallest scales, space and time themselves might be quantized, composed of discrete, indivisible units. In such a framework, the speed of light could emerge as a natural consequence of the geometry of spacetime at the Planck scale. While these ideas are still highly speculative and lack experimental verification, they represent the cutting edge of human knowledge and our relentless pursuit of truth. The journey to understand the speed of light has taken us from the hills of Italy with Galileo to the complex mathematics of Maxwell and Einstein, and now to the bizarre world of quantum fields. It is a testament to the power of human curiosity and our enduring desire to comprehend the cosmos. So, the next time you look up at the night sky, remember that you are not just seeing stars, you are witnessing the history of the universe unfolding before your eyes. Delayed by the cosmic speed limit, every photon that reaches your eye has completed an epic journey, navigating the quantum vacuum and adhering to the strict laws of physics. The speed of light is a reminder of our place in the universe, a universe that is vast, mysterious, and profoundly beautiful. And while we may never be able to travel faster than light, our minds can certainly explore the infinite possibilities that lie beyond the horizon of our current understanding. The quest to uncover the secrets of the constant c continues, and who knows what astonishing discoveries await us in the future. Thank you very much, and see you next time.